One of the problems I put on the answer sheet, the shortened answer sheet, was 945. I thought it required a little bit more explanation than just putting the numerical results, so I wanted to go through that one for you on this video. The students who had the polymer course might have done something like this, but the mechanism that you see on the slide here is basically a free radical mechanism that there was a type of in our text. In this mechanism for polymerization, you see the initiation of the process starts with this sort of initiator. It's called benzoyl peroxide. This dimer gets cleaved into two radicals. One of those radicals, when connecting with a monomer, something like ethylene or another hydrocarbon, produces a radical that begins the initial part of the chain. The chain can get hundreds of monomers long by having the initial radical bump into a neutral monomer to form a two-link chain, one of which has an extra electron on it. That's a propagation step. When individual radical chains meet another radical chain, well, that causes a termination because these single electrons can form a bond, and that basically stops the growth. But you could create chains that are hundreds long just by starting off with a little bit of initiator and then going through. One of the pieces of data we're given here is that the half-life of the initiator is 19.8 minutes at 100 degrees Celsius. And so that data is going to help us begin answering the questions that the text states. The first one is calculating the rate constant of this reaction. Let me see here. I think by that they mean the first order reaction of the initiator. So if we know that it's first order, we know that there's a very simple relationship between the rate constant and the half-life, and 0.693 divided by 19.8 minutes gives me a rate constant of 3.50 times 10 to the minus 2 minutes inverse. At 70 degrees Celsius, we're told that the half-life is 438 minutes. And I think I see a Van Hoff equation in our future, because once you're given rate data at two different temperatures, then you can find out a quantity like activation energy. So the natural log of rate constant in condition 2 over rate constant 1 is equal to minus EA over R, and 1 over T2 minus 1 over T1. Using the same equation for K that I used in A with this new piece of data, the K value is 1.58 times 10 to the minus 3 inverse minutes. So we have two rate constants at two temperatures. We could go forward to show that the natural log of, let's call the 100 degrees K2 and T2, 3.50 times 10 to the minus 2 inverse minutes over 1.58 times 10 to the minus 3 inverse minutes is equal to minus EA. We always use our energy value of R in problems like this, and making sure to keep things in Kelvin. We could finish off the parenthetical statement and solve for EA. EA in this case turns out to be, in terms of kilojoules, remember that you'll have to do a conversion there, is 110 kilojoules per mole for the activation energy. Part C says write the rate laws for the elementary steps in the polymerization process and identify reactants, products, and intermediates. If I number these steps, they actually don't number this one here. That's just kind of an initiator step. Step 2 and step 3. I could run down to the initiation step is just going to be the rate constant, which is just plain old K, times the concentration of the benzoyl peroxide to the first order. So that's pretty straightforward. The propagation step is going to have a rate that they say Kp times the concentration of the radical times the concentration of the monomer. So that's an overall second order equation. And the termination step looks like it's going to be also second order, first order in each of the monomers. So what did they call that here? Actually, they didn't have a rate constant. Let's just call it K1 just for the heck of it, or KT for termination. The rate constant for the termination step is going to be the concentration of radical 1, and this is radical 2. The difference in these primes, the single prime and the double prime, that's just referring to how long the radical chain is, not necessarily a particular length. And so all of these rates are written in terms of, let's see, radicals really probably should be considered as intermediates. And if you wanted a real numerical value, you probably should make a substitution for them based on an earlier step. One of the last pieces is kind of a narrative type question. It says, what conditions favor the growth of long, high molar mass polyethylenes? This all has to do with increasing the number of propagation steps that happen before termination steps can happen. And so that would seem that long polymers are going to be favored by high concentrations of monomer and low concentrations of the radical, the initiator. Because if you have a lower concentration of possible components in the termination, that's going to increase the length of these things. So I'll do a couple more of other problems, and good luck following along.